So, okay, so 3 things tonight. We're going to go over the exam quickly. I'm going to do lecture 8, the beginning of the second half of the semester, and then I'll go over a couple of the homework assignments. I won't go through all of them, but the next couple, just so you have an idea, and they'll start being due. I think first one's due next week. I suppose I should have checked that, but I don't have it up here, but I'll tell you by that time. So quickly on the exam, the average was kind of high. Maybe the final will be a little more difficult. I wouldn't say it's going to be tremendously more difficult though. So why is the verification of design only possible if design under verification is correctly specified? Because verification is seeing if the design matches the spec. So that's simply what the answer could have been. Maybe some embellishment on that. 2 different characteristics of the specification that contribute to successful. It has to be clear, it has to be complete, right? And then offshoots of both of those things. Well formatted. I took a lot of different things. There's some wrong answers there as well. The consequence of the specification changes during the verification process is time and money, right? I took that one right off the bat, but other things are that one of the groups gets the change and the other one doesn't. So that wastes time as well. Who should review the specification? You had to say the design group and the verification group. I wanted other things though, and anything, marketing group, software group, anybody involved, but it has to be the design and verification group. If you just said the verification group, lost points on that. Difference between static and dynamic. The easy answer, stimulus. Static verification doesn't need stimulus. Dynamic verification does need stimulus. You know what? I didn't give the codes. I'll do that when I'm done. Behavioral. Static verification tool, context sensitive editor, or lint. Those are the big ones. Dynamic verification tool is the simulator. Behavior extensions improve test bench design. This is kind of a vague question, and I took vague answers on it. But simply, it takes things that are verification oriented and makes them easier because you don't have to worry about them being synthesizable. And then UVM, the easy part of the answer there is bring things to a higher level of abstraction, right? So you don't have to do a lot of detailed coding. In addition to that, it's the formatting, right? The fact that it also imposes a set of coding guidelines on you. Black box modeling, you don't see anything but the inputs and outputs. White box modeling, you see the inputs and outputs and everything inside. Gray box modeling is you see the inputs and outputs and some of the stuff inside. The one that we want to use for verification, we'd love to use black box modeling, but that's not practical. The practical one is gray box modeling, dark gray, right? Close to black box modeling, but the answer for that is gray box modeling. Difference between behavior modeling and RTL modeling applied to verification systems. So the easy answer is RTL modeling is the dot. Everything else can be behaviorally modeled, and maybe there's RTL in there, but we don't have to worry about synthesizing it. 3 types of models. So there's other answers for this. The stimulus model, the device under test, and the response checker are 3 types of models. So there are other models that I picked, or I accepted other answers. The only thing I really didn't accept for this, and this was one of the harder questions actually, if you gave me something that was one of the 3 and it wasn't a model. So if it was a model and it found its way to the test bench, then it was one of the 3. My thinking was stimulus, dot, and response. There are others, and if you used one of the others, that's okay. If you put something in there that wasn't a model, you got it wrong. I would say of all the questions on the exam, that had the low, if I tallied everything across questions, that would have been the lowest score. Why is configuration management important for verification? This was actually one I went back and I gave people points back. This is why, because the verification team needs releases, their customer. So they need to have a baseline for running tests. And then when they find bugs, they report those bugs against that release, right? That baseline. So the connection between the design team and the verification team is that release. So that's why I said, all right, maybe if you didn't say release in the first one, you're confused by the fact that the next question was specifically asking for you to say release. Name and describe how issue track is integrated into the configuration management process. Kind of what I just said. You report bugs. You report them against releases. The designers look at those bugs and they look at them relative to the releases that the bugs were reported on. And then for D, I wanted to see the states. So as an example, open, fixed, verified, closed, if you were. So you just had to kind of show that bugs go in different states. It didn't have to specifically state the ones that I just said. Most important question on the exam, and basically this was it was easy because I think I stressed it enough. Code coverage tool is important to the use of constrained random stimulus. And the reason is you don't know what the stimulus actually is because it's random, but you need to know how much progress you're making. And code coverage tools show you how much progress you're making over time with constrained random stimulus. And then once you run out of gas, once you've covered everything you could possibly cover with constrained random stimulus and you have things that still aren't covered, then you write a directed or targeted test case, and that's the one that goes in and covers the things that you're not covering with constrained random test. And that was, that's the interview question for you, those two, at least in the first half. And then if you don't have 100% coverage, you're not going to be able to fully verify because you haven't exercised the whole system. If you do have 100% coverage, it doesn't mean you're fully verified. It just means you have the potential for being fully verified. Okay, so I handed the exams back a while ago. I didn't hear from anybody, meaning I added wrong or something like that, which happens. But if you do have a question about the exam that maybe your grade isn't right, I'd like that to be closed by March 23rd. So you have 1 week to hear these answers, go back to your exam, think that maybe I didn't, and then you simply just send me an email and tell me, don't try to re-answer the question or change your answer. I have all your exams, obviously. So just send me an email saying, hey, I think this is wrong. Or could you add that up again, which happens sometimes as well. Okay, so that's that. The codes. Okay, so for the in-class, 2189. So the in-class attendance code is 2189. Go back. The virtual code is 4406. So if you're in the virtual, 4406. Okay, I'll bring it up again at break. Okay. So I have been promising to talk about behavioral modeling for a while. And hopefully it's not disappointing to find out that we kind of have been talking about it, but we'll formalize that tonight. So let me just get to the slides. Recording. All right, we're good. So behavioral modeling is modeling like everything else, except we don't have to worry about synthesizing it. We call that RTL modeling. RTL modeling is input to synthesize and produces gate level. So behavioral model simply is a case where we're writing code, potentially with the same languages, but we don't have to worry about synthesizing it. So use System Verilog for RTL. And we're using System Verilog for behavioral modeling, conventional Verilog, either way. VHDL, same thing. You can use VHDL for RTL, which happens a lot. And you can use VHDL for writing behavioral models for test benches. That's not that common, right? System Verilog is the much more common language for test benches, and that's partially because of UVM as well. So as a review, right, synthesizable code is RTL. Behavioral code is our test bench. RTL code is the kind of things that we want to develop for synthesis. So we're building architectures, and that's the other class. That's the FPGA class. But in simulation, we still have some things that we have to do, right? It still has to have at least an interface to the DUT that looks like a digital system. So we're still going to use the kinds of constructs that we drive the DUT and receive things from the DUT that we use in the DUT. But everything inside that, we can use constructs that we don't have to worry about clock edges per se. We don't have to worry about big math things. We don't have to worry about not using floating point and those things that would really not be synthesizable. We could do that. Now, lint tools will tell you if something is synthesizable or not without having to go through the synthesizer. So we worry about that in synthesizable code, but we just worry about functional correctness in behavioral modeling. So as I keep saying, you don't have to limit yourself to synthesizable code, right? Anything is fine. There's no need to build a hardware architecture. And really, when you talk about behavioral modeling in a class like the FPGA class, I think you've all taken the FPGA class, right? Have you taken the FPGA class? We kind of use behavioral model as the predecessor to writing the code for the RTL, right? It's the architecture part. We don't have to worry about that here. So we're writing behavioral modeling here to make the job, I'll say easier, but to give us more capacity to what we need to do in the simulator. We get another piece of that. Because remember, when we talk about simulators, we say behavioral code runs faster in the simulator than RTL code. And the reason for that is it has less detail. And remember that RTL code runs faster than gate level code because RTL code has less detail than the gate level code. So we're staying to the point where the designer doesn't have to worry about the architecture, but the simulator also doesn't have to worry about building things in the structure of the code. So we speed up in two directions. And we want the verification process to be easier because potentially in the verification process, we're redoing everything. In fact, we might even be redoing everything twice because we have to model all the stimulus and we have to model the response so we can check it. So we want to be able to take the shortcuts of not having to model what the architecture is going to look like inside the chip. So more efficient, more compact, more flexible, and it simulates faster. Right? So they were all. So no synthesizable restrictions. There can be consequences of bad code. So what are that? So we know what the consequences of bad code in RTL are. And for the most part, that's things like simulation synthesis mismatches. Cases where we're not really getting what we intended to get. Things like latches, like tri-state buffers that aren't going to go in something like an FPGA. So you think, well, in behavioral code, we aren't that worried about the architecture. But when we don't have the guardrails of synthesizability, and you open it up to more of the language, then you run into problems that you'd run into in more of a high-level language type programming. So, to pick things, we might create very complicated memory structures in the scoreboard, right? So in the test bench, we might create very complicated memory structures. Well, very complicated memory structures have problems if you don't design them carefully, right? You overlap things, you overrun the records next to other records. And if you don't have that nice sharp structure that you would have in the RTL, you can run into problems. And the problems are maybe even hard to find because I know me and I do more design than verification, but I do a fair amount of verification. When something is wrong, what do I think is wrong? The software. No, just kidding. I think the RTL is bad because I'm testing the RTL. So if something doesn't go right, it must be in the RTL because how could the test be wrong? So when the test is wrong, it's harder to find, right? It's the second in priority when you see something not work right? You tend to focus on what you're trying to test. So if you put a meter on a battery and it doesn't measure the right voltage, you suspect the battery. But if the meter had a problem, that would be the second thing you looked at, right? To make it a very simple example. So that's something to remember. That's a consequence of bad code in behavioral coding and in test bench design, but it's the same thing right now. When we write this stuff, we're making an investment. And why do I say this, right? Write maintainable code, not disposable code. We always think about that, and we think about that in reusability type things. We think about it in RTL, but in test bench design, why is it valuable to write? Why is it even something we think about to write disposable code? Because once the test is done, you don't have to go back to the code. Look, it passed, I'm all done, right? Just like school, right? You pass all your finals, you forget that whole semester, and you go on to the next semester. Well, here, you are making a big investment. So if you do a good job with the code, you can use that not only for new things, but derivative things. Probably should have said that the other way. You can definitely use it for derivative things, but if you're building a very well-designed, say, I'll pick an easy example, SPI interface, serial peripheral interconnect, if you write a really nice piece of behavioral code to test that, you got something forever, right? You might have to enhance it for other features. If you write some disposable code, what happens the next time you write, you need to write a test for a SPI. You're either rooting through the trash for what you disposed of, or you're starting over. So don't ever think that something is so unique to what you're doing that it's not going to be reused, right? That's the lesson of developing product lines instead of products. I always think that this is the first product, and I'm going to build on it and create a second product from it, a third product. Even if they're revolutionary, some of the things at least give you a head start. So an obvious statement is write maintainable code, not disposable code. I want you to just remember why there's more of an attraction to disposable code in behavioral coding or test bench design. So saving lines can make code worse. Just as a statement, that should maybe be more in the coding guidelines. It's not as understandable. They say less code has less bugs. But one thing that I can pretty universally say is they don't take carriage returns out of your pay. So space your code out, give yourself some room, give the reader the ability to see it. Good commenting is good. Again, sometimes in behavioral code, it's behavioral code, it's self-documenting. No such thing. Comments are good. And if it's not applicable to what you're doing. So we know what the structure of RTL is, right? But what's the structure of behavioral code? Right? If you take that FPGA class, I told you exactly what the structure of a flip-flop was, exactly what the structure of a mux was, exactly what the structure of a state machine was, and you built out from there. I don't have that answer for behavioral code because the reason I gave you those structures is because I know the synthesizer would take those structures and they would build exactly the gates that we wanted them to build. We don't need that here. So the structure is a little different. And again, I'll use that same example. It's structured more like high-level code, like a C program. But it always has to be some structure. So my advice there is look at UVM. Right? They're not structured from an RTL standpoint. And there's really no equivalent, by the way, to UVM in the synthesizable world. Wouldn't that be nice, right? That if you had something that gave you high-level constructs that you could write that would generate RTL for you, it doesn't really. People think they exist. They think they're selling them to you, but they don't. You can buy a UART, you can buy a SPI interface and latch them all together. But if you want a state machine, you're taking the construct that I gave you, or maybe something that will allow you to graphically input to it. So take advantage of the kinds of things that UVM would do, right? Consistent interfaces, a consistent kind of hierarchy. So what did I stress before, back when it was cold out? Oh, it's still cold. That there was bus functional models, test cases, and that's what ran in the test bench, right? That's a really nice top level architecture that if you stay strict to, and if you didn't do this in the homework, you heard about it, that gives you a really nice structure for that. Now within that, you can do whatever you want, right? And do whatever is best and write it more like high-level code. Encapsulation, encapsulation is bus functional models. So these are these from the book. Some maybe programming concepts more than anything, and sub-programs. And really, we want to talk about this more in terms of where things go. And it's up to you. And I surely didn't put requirements on the homework, but the homework that you did, homework 4, you wrote a few bus functional models. And in reality, I would have liked you to write those in a package. And then that package would be the package for that DUT, meaning it had all the interfaces that DUT needed. If I had a different DUT, it would have a different package with a different set of BFMs. Some the same, some different. And so that would be like your package for the bus functional models. Then you have your test cases, and the test cases call bus functional models, right? That's what you're going to do in the next homework. You're going to call a series of your bus functional models. Well, you have a bunch of test cases. You could have 100 test cases on something that's complicated. It's just an example. And those test cases are going to get more complicated to the point where you're not just going to list a bunch of calls to bus functional models. You're going to create, I'll call them macros, that are groups of bus functional model calls that do things. So let's say you have to initialize the chip. And that's obviously the reset bus functional model, but you might have to write a bunch of registers. You'd make that its own routine. I'll call it a macro for now. And now every test case, a lot of the test cases, we'll say, would run that initialization routine. So all of those next level up would be in its own package. And then test cases are test cases, right? Those you just got to run as test 1, test 2, test 3. But just see how that structure is going. And whatever makes sense. You don't want to have a lot of structure here, a lot of hierarchy. You want to keep it fairly thin, but the bus functional models are always there. The test cases are always there. If stuff gets complicated, you might do things to bring that middle piece to a higher level of abstraction. So there's bus functional models. And one thing I've ignored, and I'll just mention now and then get back to later, is reports. So reports, what's important there? Well, you need to collect data from everything you do, even if it passes. So I suggest that you have, for every test case you run, a text report. And the report can show the progress of the test. And the last-ish line in the report is test passed. Potentially, it could be test failed. But it gives, even though it passed, it gives you the information, because sometimes you find out later that a test passed, but it didn't really run. So you have that in the report. Disk space is cheap. And we're not talking about, terabyte files here. We're talking about things that are 100K each or something. So every test case has a report, and then you have a report for every run. So when we start to talk later about regression testing, which is where we run all the test cases over and over, we have another report that's the report for all of the tests that were run. So it's not as verbose as all those separate reports, but it takes the important details like test 1 passed, test 2 passed, test 3 passed. Test 4 failed, and this is why it failed, right? We don't need reasons why tests passed, but we need reasons why tests failed. And then no global variables, right? The languages just don't work that way. Okay, so we've talked about it. We'll keep talking about it. But here's the bus functional model. Bus functional models come from you. You know that. You did that in homework 4. They come from third parties like this. So this is PCI, for example, right? It's maybe a little old example, but on one side, on our left, is the functions that you would use to call this, right? The task calls. And on the right side are the pins, right? No surprise. So this is something that you would likely get because PCI is a standard bus from a third party, right? And most likely a third party that was also selling you the IP for the PCI that you're putting into your design. I always caution you on that. There are providers of VIP, verification IP, who will sell you bus functional models. And I would say it's pretty certain that the IP that you get with the verification IP or vice versa is going to work. But all that tells you is the test that they ran on their stuff passes. It's nice to have a little independence there. Sometimes you get these things from processor manufacturers. So I think I used the Intel example earlier in the semester, but they're not going to give you a HDL model of their processor because you could synthesize it and build it. Of course, you'd have to go to them for the fab house, but so they don't want to do that. But of course, worse, you could go in and find stuff, right? So maybe the whole processor isn't valuable, but there's lots of pieces in there that are. So they give bus functional models, and it's a case where if you have 10 different transactions on the bus, memory write burst, IO write, just to make some up, you'd be able to call a task for each one of those. And they want to give this to you because they sell processors because people build peripherals for them. That's not completely true. They sell processors because people write software for them. But in our case, they want people to write video processors and things like that are going to go on those buses, and memory controllers or memories themselves. Okay. So now that we put this wedge in between the DUT and the tasks, we've abstracted the data. Now this is, you remember when I talked about math? Well, this is important for similar reasons because we're describing what we want the BFM to do in human-like terms, in test case terms, but we have to know that it's coming out bitwise the way we want it, because that's what the bus functional model does. It translates from a high-level request to bits, right? The bits on the DUT. So when I said earlier that you could use things like floating point inside the test case, how does that translate when it goes through the bus functional model? Well, you have to fix it. You have to do something with it so you know that the behavioral stuff you did within the test case comes out to be the right signals, the right function on the bus. Okay, that's one thing, right? Because you don't have to do ones and zeros on the bus functional side, on the behavioral side, but on the bus functional side, you do. It has to be logic, and I stressed that half hour ago, maybe less, that's what the bus functional model does. Okay, that's one piece. The next piece is when you're using the bus functional model, and I'm going to say something and then say something different that has the same result. When you use the bus functional model, you're looking at the bits that are going to happen, but you're telling it you want to do something. And if it's something complicated, and it says SONET here, which is a synchronous optical network, but it could be Ethernet, it could be anything. We don't send bits to that, and we don't even send bytes to it. Now we could, and let's say we sent bytes to this thing that allowed us to have 1,000-byte messages, and we could send it a byte, a byte, a byte, a byte. And the test case would say, I want this byte and this byte, and send all those things. And that would be the first bullet where we're taking those numbers and we're converting them to digital bits along with the control signals and sending that in as a message. Do we want to do that? I don't think so. What I would rather do, and this can be another level of abstraction, this can be encapsulated over the bus functional model, is say, I want to send a message. I want it to be 1,000 bytes long. I want it to have random data in the payload. I want this to be the destination address, this to be the source address. And that's how I call that task with all of that information. So from there, it constructs a message. It calculates a CRC. It might send me an error if I did something that's not legal, if I told it to send something that was too big or something like that. And all this is done within the task. So this is where we talk about, and it's part of abstraction, thick versus thin. I'm sorry, I slipped that. A thick interface versus a thin interface. So a thin interface is one where you're basically telling it what to do and it doesn't, right? Send this byte and sends that byte. That's a thin interface. And there's a lot of advantages in thin interface because you have the most control over a thin interface. But it's more work for the test case. A thick interface is one that you give higher level information to, and it has more responsibility. So one thing I said as I was talking about this is it calculates the CRC automatically. Well, isn't that great? Because it took the burden off the test case until you wanted to put a bad CRC in. Oh, wait, the bus function model calculates the CRC automatically, and I want a bad one. So what you just did is you added another bit in the interface to the bus function model that says bad CRC. Okay, let's extend that a little bit. So we have in this message, I rattled off source address, destination address, length, whatever, a whole list of things. We're also going to put, if it's this kind of more functional bus functional model, we're going to put things like error insertion. We're going to put randomization in. So when I said that I want a payload with random data, that's a flag that I send across this task call that runs a random number generator in the bus functional model. Now, what you've seen, my example, the FIFO example, and what you're going to do, not next time, but the time after homework 6, is you're going to call your bus functional models with the random number generator. Because this problem is just too simple to not do that, right? It's not a big deal, right? It's just sending single bytes anyway. There's no protocol on it. But you can see now the type of things that you would add to this higher level of abstraction bus functional model. So the sending of packets was simple. Now let's extend this because remember the stimulus and response. So on the response side, what do? So on the response side, we run a monitor that's running forever. So it sits there and waits for packets to come out. And when the packet comes out, it might take a byte and send it to the test case and so on, right? That low level thin interface. But if it's the more functional interface, the thick interface that I'm talking about, then what it's going to do is actually receive the message, decide if it has a proper destination address, a proper source address, right? You get the idea. All of the stuff, it's going to check the CRC, and then it's going to produce a result to the test case that says, I just got a message. This is when I got it. The payload was random, or maybe you do a check on the payload. The CRC passed. This was the source address, and this was the destination address, just as an example. So now the test case just monitors this bus function model for good and bad packets. Now, I think that if I have a scoreboard and I'm generating packets at that high level, that I also want to get a high level result to go on the other side of the scoreboard because I'm trying to match those data structures. And in fact, I'm probably, and I don't want to say always, going to keep the format of the input, the stimulus bus function model, the same as what comes out of the receiver, right, the detector. So when I check it in my scoreboard, I'm simply just looking for records to match. So how do you make this decision? Well, the first answer is it might not matter, but the real answer is you kind of go with the system architecture. So when I start thinking about Ethernet packets, for example, I think of all of the fields in the Ethernet packet, and I think if I was actually building a Ethernet media access controller, a MAC, and I wanted to send a packet from one to another, that the processor, the thing that was writing the packets that were going to be sent, would write it in a big record, the bunch of fields that I've been saying all day, say, I'm ready. The Mac would go and get it, and it would format that packet, send it out, and it would end up in a memory structure on the other side that had all those, a record with all those fields, that I could potentially take that record, right? If this was a networking class, I'd tell you about how you would take that new record, the one you just received, change some addressing around and tell a different controller to send it, right? That's how networking works, right? We don't handle messages. We handle records that have messages in them. right? So for this case, just think of it that way. Okay, let's talk some more about this. What if I had a processor? How do you test a processor? What could go wrong in a processor? So if you've taken a computer architecture class, you know it's pretty easy. Right? If you've taken, the MIPS class or the RISC-V class, whatever they're on here, I know when I took that class, I couldn't wait to write the Verilog for it because it wasn't that big of a deal. A RISC processor is pretty easy. It has a register set, but it's well thought out, right? So the register set has all the right size things to give you addresses and do math. And then the ALU, you can copy the code right out of the book. And if you don't want to do this, you can just download it because it's like, you know what? When you come to Draper as a new hire, you have to give a presentation. I am so sick of students coming in and showing me the RISC-V pipeline for their presentation. I tell them, if I talk to them on the phone, right, pre-screen them on the phone, I say, don't tell me about the RISC-V incoming presentation because everyone has seen that. But it's really good exercise to do it. So what could go wrong in that? Well, a lot of stuff could go wrong, right? I could have mistakes in the state machine. I could have addressing that isn't quite right. I could have race conditions. The place where things really go wrong in a pipeline processor, if you aren't familiar with this, when there's things in the pipeline that are producing results that things behind it in the pipeline need, but they're not ready in time, you have what's called a hazard. And there's different types of hazard. Hazard where the data isn't there, which is a data hazard. Hazard like a control hazard where you had fetched instruction, but then you did a branch and you didn't need that instruction. And there's other things, and there's things that you can do to fix it, like to stall or to forward results or to prefetch things. Sorry. I'm not a teacher in processor design, but how do you test it? Well, you write software that specifically creates a hazard in the pipeline. I don't know how to do that because I write C and the compiler writes the machine language for me, and then I run that and it works or it doesn't. I'm a designer at that point. But what if I want to verify a processor? So what I need there is a generator of random instructions. So I have something that generates legal, maybe most of the time, legal instructions. And every time the program counter goes and gets something, I take random next instruction out. So now what I'm doing is I'm testing the order of the instructions. And I'm doing it randomly because if I had to write targeted test cases for every one of those, it would take forever and I would bias it all over the place. I randomly generate instruction codes and it processes those properly. I have a model of the processor that tells me for a given set of instructions what the results should be, and I compare the results. Maybe I just compare memory at the end. So now my abstraction is something that randomly creates instructions because instructions have 5 fields in them or something, right? Destination register, source register, operand, all that kind of stuff, opcode. So I'm generating instructions with separate random, constrained random variables that dump things in, and then I'm checking to see if it works. Just to continue with this thought experiment a little away from what we're talking about here, I would do that for a really long time. And then I would look at the coverage. And if I went and looked at the coverage, I might see that a signal in there called forward, which is a thing that forwarded data, if there was a data hazard. If I saw that was uncovered, then I would have to write a directed test case that would be a sequence of instructions that would specifically, and you can copy this out of the textbook, that would specifically cause a data hazard that would cause that forwarding signal to go active. I'd be pretty suspicious if that happened, but still, right? That's the kind of thing that constrained random stimulus and functional coverage tells you to go and write a directed test for. Okay, so we covered communication type things, packetized things. We covered instructions, and we got one last thing. And it's not the last thing, but it's last enough for our discussion here. I think there were 3 kinds of systems in the world, and all systems are a combination to some extent of these 3. There's communication systems, there's processing systems, and there's signal processing systems. So processing system is the computer architecture thing. The signal processing is I put in data and I filter it and I run fast Fourier transforms and I decimate it and all these buzzwords of signal processing get a different signal out. So how does that work? What does data abstraction there mean? Well, it's more difficult because we can't randomly inject data into that because we'll get noise out, right? So I can't just randomly come up with a bunch of bytes. So I have to figure out what random really means. So let's take an easy case, fast Fourier transform. And I put in a sine wave and I get something that is at that frequency in my spectrum coming out of the fast Fourier transform. Am I done? Right? I've tested that it probably works, but I haven't verified that it works. So what do? Well, I move it. Right? Put that sine wave, change the frequency of sine wave, see that go, try the edge. Maybe I even randomly move it, modulate it, I guess those guys call it. But then what else do? I add things to it. I add randomness to it. So I add a noise generator. So that thing now looks like this. And when I have this random generator, and this is one function, which is rare, right? There's usually filters and other things in the process, but let's say I just have that one thing. And I get the spec maybe for what randomness looks like in the midst of the signal. Maybe I stand outside with an antenna and gather data, right? Because that's more I try not to say more real noise because noise is noise, but you get the idea, right? It's more the type of noise that you would see in a real system. And then I do that, and then I maybe have a filter on the other side that's in my test bench, right? So my bus functional model in the receiver has a filter in it that takes that noise out to see that I still have my fundamental signal. Or maybe I have a notch filter that takes the fundamental signal out to see the profile of noise to see if it's the same as the profile of noise there. Right, so this is a little less conventionally constrained random stimulus because I have to be a lot smarter about what the randomness is. Because you put random data into a signal processing system, you get random data out. Right? It's very difficult to find that. But if you put real stuff in and then randomly inject noise or errors, that can be an interesting thing, and that can actually kill you in real life. Drop the signal out, right? So we all think of that, okay, I have this little white noise generator or, pink noise over spectrum, and we add that to the signal and we see that it gets the right thing. But in reality, we do see that, right? The air waves are full of that kind of stuff. But reality is also full of missing bits. So one thing that you might do in a signal processing system is randomly set the data to 0, set it to the highest point for 8 samples in a row or something like that, or a variable number, and see what happens, right? Some of these frame-based FFT things go crazy with just a few bits missing out of the frame that goes into them. So digital signal processing is harder for the type of thing we're doing, because ultimately you're not modeling something digital, right? You're modeling an analog system. But for the other cases, the communication case, that constrained random stimulus packetized model, perfect. Processing, it's maybe a little lower level, it's also perfect, yes.
If your DSP was doing a digital demod, could you treat it like a communication test?
Yeah, so So the question is, if the DSP signal was doing the demodulation, could you treat it as more of the random case? And I have 2 answers for that. Yes, absolutely, and no. And the no means, what if the impairment on the signal caused the modulation to mess up? You'd want to know that. And a lot of times, let's say it's quadrature, so you have 90 degrees. Is it, where's the detection area of that angle? But yes, the first answer is absolutely yes. And it will tell you, because you're effectively converting it back to digital, that it works, and you can put noise on it and see that it still works. But you also want to modulate it a little bit to see if you get it across. That's a good question. So real values, floating point, MATLAB is your friend in signal processing system, except MATLAB doesn't know anything about digital. So when it gives you a file remember that sine wave I talked about in the middle, where did that come from? Well, it probably came from MATLAB, right? And the noise probably came from MATLAB. Well, it's probably, some fixed point thing, not 32 bits or 16 bits or 12 bits or whatever your signal processing chain is. So be careful with that stuff. And you might even just need to test it, right? Test without your DUT in there, see that the signal coming in gets treated properly by your detectors. So real to fixed point conversions have to be done rigorously. Sine kills you in this stuff if you don't get it right. Records I talked about. Verilog records are not objects, but they appear to be. So don't think of records in the Verilog sense of records. Think of records in the generic sense that a record is a piece of data that's made up of fields. How that actually gets coded can vary a lot. Whoops. Multi-dimensional arrays. So this is verification class. We'll talk all we want about multi-dimensional arrays. Verilog supports multi-dimensional arrays. Isn't that nice of them? Guess what doesn't support multi-dimensional arrays? Hardware, right? RAMs are not multi-dimensional. So it's basically considered non-synthesizable to have a multi-dimensional array in a circuit. Now you might think, well, I wrote this multi-dimensional array and I synthesized it, it was fine. Well, maybe one of your dimensions was 0 to 3, right? It was only 4, and it put in 4 memories for you. But a true multi-dimensional array is not synthesizable. But if you think of something like the scoreboard, you really need something like that, right? You need more than just the address and data on it. You need another dimension to search on, and it supports that. So you can't use it for the DUT. You can't use it for synthesizable, but in this world, fine. Behavioral code, multi-dimensional arrays work really well. Remember that when you produce an array in the DUT, you're building it. When you produce an array in the simulator, it's more virtual memory. It's more like, you write C code and it allocates memory for a function call, and then the function calls over, it gives the memory back. But you can't do that in hardware, but you can in a simulator. So writing these things properly, writing them as objects will manage your memory. And then remember, this is also running on an operating system which does memory management anyway. I have not specifically tried to find out what the limit of things like model sim are in terms of how much memory they'll let you allocate in the simulation, but I've never been careful of it and I've never had a problem. So they do a really good job with memory management. So a list is a single dimensional array, right? A RAM is a list, right? Not too interesting for us. Files. Files are definitely behavioral. You can't write to a file inside the DUT. You can't print out within the DUT, right? It has to all be in there. It has to be stored in memories. But files are behavioral code that you can use in verification. So I've already talked about this tonight, and that was the log file. So when you have data that's coming out on the console, you save it. You put it in a file. You give that file a unique name or an interesting name, something that has the test case in it, maybe the date and time or whatever you need in the file name. And that's one application. It's kind of an afterthought, right? It's the end of the process application, but what else can I use files for? I use it for all kinds of stuff. So that MATLAB thing, right? The stimulus and maybe even the response, that was a file in and a file out. And I could have a library of those files. And we have systems that we use for communication where we do field testing in them, and we just gather. They bring like terabyte disks with them and plug them into the computer, just fill them. And they're walking in the morning, people want the disks because they can make it part of the simulation. It's great. That's how you find errors. So the stimulus can be in a file, the response can be in a file. Obviously, the code is all in a file. That isn't necessarily. But another thing too is test cases aren't always just a bunch of calls to BFMs. Sometimes you can have multiple test cases that are the same calls to BFMs, but different sets of information of how you go through those test cases, control files that give you that. So use this stuff to your advantage, right? Don't print gobs of information out to the console because it's impossible to look at. And what do you do when you do that? You end up copying it out of the console and pasting it into an editor, which is clunky, and sometimes it only stores so much. Everything should just go to a file. And I know I do it, and I know I show you doing it. Do what I say, not what I do. I never put a display statement in my test that displays to the console. It always goes to a file, except maybe for one at the top that says test 1 started, and one at the end that says test 2 passed or failed. But all of my informational stuff within the test goes to a file. And I make sure that I name the file correctly, at least with the test name, probably with the date and time. And the reason for that is it's not out of the question that I've run that test over and over. And I want to keep those files for everything. And, I do occasionally get, the knock on the door, the email from IT that says, what are you doing? And I, create a date and delete everything before that date. But for the most part, this stuff is cheap in terms of how much data. So everything should be files. Okay, so still time. So the HDL parallel engine. So when you write RTL, if you put 4 state machines in your design, right? We're thinking as an RTL engineer, and we're doing something, and we have 4 different state machines. We write those 4 different, this is what software people like leave this class, well the FPGA class. 4 state machines, you compile all of them, you put them on your FPGA, and you turn the FPGA on, and every single one of them is cycling on every single cycle. They all run at exactly the same time. And this isn't multiprocessing. It's not massively parallel processing. It's digital logic. That's how it works. When you model that in the simulator is sequential. It's running software. It's running step after step after step. For the most part, I know that hardware accelerators don't work like that, but let's just humor me for the short term at least. So there's advantages in knowing that you do have sequential execution in the simulator, and you can write your parallel code such that it runs more efficiently in a concurrent environment. So what the first answer is, and I'll pick the easy, you only have 1 clock. So the behavioral model that generates your clock, and you've seen it a bunch of times now, you saw it in the RTL class, you saw it here, it's inverting. That is the clock for everything. And now when you go through your tests, and even though it's a sequential test, you're gating it, don't gate it by putting in times. So you see, pound 40 or pound cycle or whatever it is. Don't do that. Say at pause edge clock within your tests. So now they all become, I'll use the word, concurrent with that clock, but the simulator has a much easier time sorting that out because it's sorting out based on one event, not a bunch of timers that you spread out in the design. So there are other tricks for specific cases, but just think of it that way. The less triggers you have, the more efficiently a sequential oriented simulator is going to simulate your concurrent code, your concurrent design code. So concurrency is the ability to run multiple tasks at the same time. And in software, they create threads and all this kind of stuff. Well, maybe threads in a multiprocessor environment, that's real. But it's all the illusion that things are happening at the same time, right? When you're moving your mouse and seeing the cursor move on your screen, it appears that that's concurrent. But it isn't. It's sequential. Something gets sent, gets interpreted, gets translated, gets sent to the video, and it makes the cursor move. It's just so fast that you don't, well, usually so fast it doesn't matter. So it's appears to be a concurrent system, but it's a sequential system. When I have 4 state machines running on the same clock in a digital design, they are truly concurrent. That I can put in a stimulus on 2 of those state machines, and they will both go to the next state on the next clock based on that new stimulus. That's also synthesizable code, right? Concurrent code that runs in digital logic is synthesizable by definition. In behavioral code, you are running it sequentially. I don't know if I did a good job. Concurrency problems are difficult to describe. I think I did an okay job describing a simple case, and it's difficult to execute, right, in the simulator. Yeah, I think I said all this. We have a process statement and an always statement in RTL code. We know that. So this part down here is not, these last 3 bullets are not behavioral code. Right? It's just a contrast there. Parallel processing. Here's an interesting thing. I think, so I remember there's a slide out of order here, or some slides that are later that should have been here. We'll get to them. So how does the simulator deal with this? 2 things and only 1 time to look at them, right? Multiple things and only 1 time to look at it. So what the simulator has to do is say, okay, I'm not done with that, but I'm not going to increase the simulation time. So simulator has this clock that keeps increasing over time, and your internal clock and delays and all that happen. But when 2 things happen at the same time in the simulator, it can only calculate 1, but it knows that they're concurrent. So it has to put off that calculation, but it can't advance its real time. So it uses delta cycles. So delta cycle says, I'm not done the calculation, but I'm going to put that calculation at time delta 1. 1, 2, 3, 4. I keep my, I'm still at 1100 nanoseconds or whatever the time in the simulator was, but I have to go a delta time and a delta time, right? To not advance it, but to keep adding to it. And then when all the delta times are depleted, then I can advance potentially to the next clock cycle, right? The next period of the clock. And that's what delta time does. And you occasionally, 2 times you see delta time. If you look at like a list file in Model Sim, it'll show you the delta time. And when you look at the delta time, what I see in the delta time is if I see big numbers, if I see a delta time of 10, I bet I have a path in there that has too much logic in it. And I don't do this as a hobby, but if it catches my eye, I'll do something. When am I going to find it? I find it in synthesis, right? When I can't make timing on it. But the reality is, when I see it in the list file, something's wrong, right? The other time I see a delta time is if I have a combinational loop with no delay. Now, combinational loops are bad, right? It's not good design practice. I'll give you one example, but generally it's not good design practice. And when you're doing your 0 delay simulations, your RTL simulations, what can happen is that loop now just keeps trying to change. So you have 2 inverters, for example, and then this one changes, it causes this one to change and this one to change, and the delta time increases quickly. And the way you can tell that is you run your simulation and it goes dead. And you hear the fan turn on the laptop, like, this thing is really trying, but I'm not seeing it advance. The simulation time isn't changing. And then all of a sudden you get an error on the simulator that says delta time exceeded. And for whatever reason, the delta time in Model Sim is this gigantic number, like 30,000 or something like that. It takes it some time to do it. I've done it. And you have a problem. You have delta time. Now you have 2 choices there. You can fix that, but if you need it in there for some reason, then you have to put delay. So one of those elements has to have some delay associated with it, which in reality, it will have delay associated with it. So I can tell you right now, a junior designer wrote a lot of code, and we went to the synthesizer, and it has a combination loop in it. and we have the best minds, well, me and one other, and we're pouring through his code trying to find out where this combination loop is. And we found it. We're like, we found it. And it turns out there were two. So now there's only one. But it's hard stuff. It traverses multiple files. I think of, and if you do any board design, this is why I hate board design. You have a power to ground short. I hate shorts on boards because they look like they're everywhere, right? Oh, power to ground shorted here, it's shorted here, it's shorted here. Of course it is, because they're shorted together, and you got to. There are techniques, obviously. Well, that's what zero delay loops or combination loops, same thing, right? It just everything's oscillating. You can't figure out where the connection is. Here's another example. This is important enough to dwell on. I build ring oscillators, and ring oscillator is exactly what I just said. It's an odd number of inverters in a ring, and it oscillates. And it oscillates at a frequency that means something to me. I don't want to get too deep into it. But when I write them, I write it in RTL. Now, generally, I take that RTL and I send it to a back-end designer, and they make a macro for me with a bunch of inverters, and they send me a delay file, and then it actually, but every once in a while, a mistake gets made, and the RTL gets put into the simulation instead of the macro. Because we needed the RTL in the simulation to do synthesis, but the macro has to be in there. I'm sorry, for synthesis, but the macro has to be in there for simulation. So once that delay goes away, start the simulator and it sits there dead, and then the fan starts spinning, and then I get the zero delay. And of course, I do this enough that I know exactly, before it even gets to the error, I know why. But sometimes it's intentional. But when it's intentional, you have delay associated with it. Okay, seems like a lot of time spent on that, and we'll spend more on delta cycles. The slides, I think, are the last slides tonight. Driving versus assigning. This brings up another point. Less of an FPGA point, more of an ASIC point. ASICs are generally designed where you take your logic design and you put it into a top level. So the complete logic design is at that top level. And then there's another big module, and it's the I/O. And every I/O on the top level connects to one side of the I/O block. The other side of the I/O block connects to the edge of the chip. And the idea there is, in ASIC design, you have to specifically determine for every one of those what cell you're going to use for the I/O. Right? Maybe a bunch have the same, but you have to think about every one. And if you go to a different ASIC or something changes physically, you don't want to change that core logic. You just want to change that I/O piece. So it's very common to have the top level of the chip, and in it are the I/O pads in one block, one module, I should say, and then the other module is the top level of your logic. So here's the question, and this says driving versus assigning, but let's just think about what the scope of our verification is. The scope of the verification can be just on that digital logic for most of the time. And then maybe you do a gate level, which we'll talk about gate level in a few weeks, a gate level simulation of that logic plus the I/O, because it should be about the same. And when you're at that logic level, you don't have to worry about any physical characteristics of the pins, right? You just drive them, right? And it's more conventional types of Verilog assignments, right? Driving versus assignments, just like we've always done. When you go up to the pad level, you do have to worry about things. Now, here's the easiest example, and it's the most common example, is tri-state drivers. When you look at the tri-state driver output on the logic, there's two pins. There's the output, and there's the tri-state control. Those are two inputs to the I/O block, which come out to one pin. Now, there could actually be three. There could be an input, and this is a bidirectional pin. So now that pad has three connections: the output enable, the output, and then an input coming in from the pad. So you may have to have a behavioral model of the I/O block during your behavioral behavioral synthesis. And then you don't put the real pads in because they're probably not ready until you do your gate level simulation at the end. So I don't think I explained this slide the way it's written, but that's the reality, what I just said, right? That a lot of times those pads are independent. FPGA design, you really just simulating the chip, and you don't worry as much about pads. There are special pads in FPGAs, but so I do both, right? And I never really worried about pads in an FPGA except for maybe some special cases. And I always worry about it. I always see those two structures in ASIC design. So, all right, I'll give you one last example of this. A lot of times when we do ASIC design, we do an FPGA prototype of the logic, and we take that logic block and forget about the pads, dump it into the FPGA tool and run the FPGA tool. Don't even think about the pads. Because if it didn't quite work as a pad drive strengths, I don't care on my proto board, right? On my reference design, I care about it in the ASIC, and I know those pads are going to be very different characteristics between the FPGA and the ASIC. So this is more notional than anything. And again, we could talk about this in terms of system Verilog, but let's just talk about this in terms of memories and how simulators work versus actual logic works. So if I write to something and read from it at the same time, am I getting the new value or the old value? I don't know, but I'm saying you have to ask that question. So if I have a location, memory location even, to keep it easy, and I'm writing to that location on the same clock cycle that I'm reading from it, is that output data the data that was there or the data I just wrote? I don't know what it is. It depends on your application. But you have to know that, because that's the kind of thing that could work differently in behavioral code than in the physical design. If I have two things that write to the same location at the same time, who wins? Behavioral code might act differently than the actual device. Right? So that's the first two here. And don't think of this just as a memory thing, right? That this could just be flip-flops that have this condition. Just recognize these things. And as a verification engineer, hammer on those things, right? Anyone can test a memory. Anyone can put a bunch of random data in the memory. The way to really test a memory is if you have two ports, write different data from the same, say it again, write different data to the same address on every address, and then read them out. And then do a gate level sim, do the same thing. Right? This is the stuff that might not work the same. Same with initialization. So what does this do? Sometimes simulators are very nice to you. So if you put a bunch of code into the simulator and you start running it, it works. But in reality, you can't rely on the fact that those flip-flops were zero. But the behavioral models all come up zero. And then you get into gate level simulations and, oh, wait a minute, this doesn't look the same in gate level than it did in behavioral, which is a good reason to run gate level simulations early in the process. You think of gate level simulations as the last thing that you're doing. But very frequently in gate level simulations, I always run gate level simulations, and we'll talk a lot about that in a few weeks. I find something right off the bat, and it's an initialization condition very frequently. And I think, boy, I wish I had known that sooner. Now, I do a whole bunch of other stuff in gate level sim. We'll talk about what that stuff is. But find the easy stuff early, right? And sometimes just doing the gate level simulation is work, right? Getting the right files in the right places, things like that. So it's good to not be under the gun when you're trying to do that. So remember these race conditions. So, wouldn't it be nice if we didn't do that? Wouldn't it be nice if we didn't have a case where we wrote to the same location? If you're building FIFOs, that's fine. FIFOs don't have that problem because you don't read from a location until you've completely written to it. You never write to the same location from two different places. But if you have other memories, you might have to deal with this. And it'd be really nice if you didn't, but you're not the designer, you're the verification engineer. So even if the designer didn't think they did it, as a verification engineer, you want to make sure. And don't assign at time 0. Again, that's simulation stuff. You want to make sure that the RTL, right, that the DUT is reset with the reset condition. And that's not something we can talk about here. We talk about that in gate level sim. So time. Let's take a break. So it's 7:40 now. Let's say 7:55. Okay, we'll come back here at 7:55, 15 minutes. Let me give the attendance codes. Thank you. So for, whoops, virtual is 4406. Oh,
It was 218.
2189. 2189 for in class. 2189 is in class. And 4406 for virtual.
Is there a solution of the homework 4 posted on the class website?
I don't have one.
Okay. All right.
Do you have a question?
Well, I didn't get it fully working, so in order to do, I assume I have to have a working homework 4 before I can do homework 5.
Well, if you write a credible homework 5, I'm not going to
Okay.
penalize you for not having homework 4, because I understand that happens.
Yeah. All right. I mean, I'd like to get it all working at some point, but I'll come up with something for homework 5. So.
Okay. Things get around when I start publishing them, then it's impossible to get questions, because everyone has like the history of every homework assignment I've given.
Right. Makes sense.
Okay.
I'll use a kind of unrelated question.
Sure.
Have you ever had a case where you were supporting some legacy system and you needed to buy an FPGA that vendor didn't make anymore or the company wasn't around anymore? And what kind of tests do you run on that device to make sure that it's,
I'll tell you a long story really quick. I worked at this company, had a very successful product. And the thing that connected to the bus of the product was an FPGA. They called it Plus Bus.
I remember.
Oh, you're from the other story, yeah. And that's exactly what happened. We couldn't get the FPGA, and there was a timing issue on the FPGA, so we went to a broker. I don't think you want to go to a broker. So how do you know it's going to work? Over temperature, right? That's the thing that kills you, over temperature. Do you have facilities to actually test a chip?
So I'm asking, I'm interviewing at a company that does that in a few weeks, and I wasn't sure what kind of test. So that's part of they test components that you can't buy from the manufacturer anymore for legacy systems. And one of the things that I think why they like my resume is because I talked about your class.
Oh.
So
here's an FPGA, because that complicates things.
Yes.
So you put it in a socket or put it on a I always change it. This is kind of an investigative process. That's the kind of thing that might just create some stress. Yeah, I've got a great engineer. See a bunch of check.
So, of course, after taking your class, I work at Waiter right now, and I'm trying to.
You have a lot of friends.
Yeah, there seems to be a lot of crosstalk.
Yeah.
Yeah, we.
And they're close to me.
I don't think Lincoln likes Waiter very much.
Right,
Yeah.
they're both MIT. Draper's the master child.
We'll never say we're MIT, but yeah.
Right.
Yeah. But
That's not your chat.
exactly, yeah.
You feel like you're a part of MIT, right?
No.
Oh, you're at RDCs?
We're at
Lincoln is MIT.
and if you ask us, we'll tell you we've always been RDC. I heard a story though that somebody went into kind of like the old MITRE library. They found a desk that had MITRE written, and MIT was capitalizing R lowercase. So that's like the evidence that yeah, Lincoln handed over their early warning system in the 60s. MITRE did the 60s. But regardless, yeah, my fiance and I are going to go back to the beginning, so that's what
I'm not trying to push you into it, but there's a lot of good work.
yeah.
And good people all over. It tends to be like there's a whole bunch of people come around, and there's a whole bunch of people say,
Right.
but even then, they have like these get-togethers of people come around. They drive this Boston, they get this, I drive an hour and a half to get to the meeting.
Yeah.
Like Boston, get anywhere from Russia, but
Yeah.
so, but you know, pressure.
Oh, I'll take a look definitely.
But anyway, those are kind of things.
Yeah.
And again, it's an investigative process. It's harder with FPGAs because you actually have to create a program on it. And it's easier, right? Because if I give you a processor, you have to figure out how to write it, bring it to so some stuff's easier.
Yeah.
But yes, I know the process.
Awesome. Thank you, because I had no clue how to answer that. So,
And it's a credible answer, not just a complete answer.
Yeah.
So you preface with, I have to see the actual device, but these are the kind of things I'm looking at. Right?
thank you. I really appreciate that.
No problem. Okay, 4 more homeworks. I still forgot to check when it's due. Give me 1 second. But anyway, homework 5 is to write a test case. And that shouldn't be a surprise, right? That's what we do after we write bus functional models. So you're going to take the bus functional models that you wrote and write a test case. It says write the test cases. Just 1 is fine for this homework assignment. So it should be a bunch of function calls. It should compile. If you didn't quite get the test cases, I'm sorry, the bus function models working, that's okay. Just make a credible effort for the test case. Yeah, due next week. So starting next week, 5, 6, and 7, and then 8 is 2 weeks after that on the 20th. Same thing, use Model Sim or the simulator of your choice. Send me a picture that shows me it compiles and send me the code. Easy as that, right? Use your bus function models. Now look ahead, in homework 6 is you're going to write a test case, but it's going to have constrained random stimulus. So you're going to pick something, I bet you'll pick the data, for the thing that you're going to randomize. You'll set it equal to a random variable, and you'll probably just rerun the test case that you're writing for homework 5, except you'll run it with random stimulus. You go back and look at how the FIFO works for that. And then homework 6 is to take, I'm sorry, homework 7 is to take homework 6 and write a checker. So you probably don't need to write a formal scoreboard for homework 7, but you should have something, because it's serial, right? You put something in it and that's what comes out. So you have something that looks at what's going in. The bus functional model is monitoring the output and it produces a result, and you just make sure that they match, right, with some delay. And then homework 8 is gate level. So don't worry about homework 8 for now. And that's why there's 2 weeks, because that's a little more time consuming, and I had to line it up with when we talk about gate level. So 5, 6, and 7 are very related. 5, write a test case. 6, randomize the data for the test case. 7, create a checker for it. Okay, and they're due 23rd and the 2 weeks after that. So 1, 2, 3 in a row. Okay. Next thing you know, we'll be done. I think the exam is like the 3rd of May or something like that. I'll tell you, 4th of May. Okay, so let's put that back up. Okay, switch back. Quick definition again of stimulus and response. Stimulus is the environment, right? The data that you would see from the environment, and response is comparison against expected results. So the response is what comes out of the chip, but in our case, response is comparing what comes out of the chip to what we expect. So before we really get into that, we talk about reference signals. And there are 2 reference signals, clock and reset. Clock gives us the time base, just like clock does in RTL, but it's something that we're going to use in the test bench to know when to look at the RTL. And that kind of makes sense with something I said earlier when I said don't just use delays, use something that detects edges of the clock in your test bench. And then you have a synchronous signal and you have something that's aligned. Now, sometimes you don't want to align it exactly, especially if you're doing gate level simulation. So in gate level simulation, the clock of your system and the clock of the test bench might be skewed, right? There might be some difference, some delta delay in between them, because you don't necessarily, you want to vary where you look at outputs on it. And, you know, we talked about the resolution already, the time scale stuff, and make sure that you do that. And also sometimes you always have a stable clock, but sometimes the way you use that clock to clock the output might be random in itself, right? That you might randomly add delay or subtract delay from the edge of the clock. So this is waveform generation, nothing, right? The output of the stimulus generator go to the inputs of the device under verification. This is what we'll call simple stimulus. Here's a clock. Simple way to, there's other ways of doing it, and I don't care, they all work. Pick one and use it everywhere. So every clock in your system that you're generating should generate the same way. If you want to use this, great. If you want to use one of the other ways, great. Use the same way all the way through. So there's the resolution. Parameterize the cycle, and then it's high for cycle, low for cycle. There's a preference to this other than the one that inverts, because the one that inverts, if you get it into an X state, it stays in the X state, because invert of X is X, but this one is solidly putting it to 2 hard states. Also, be careful of the division operator. The division operator is biased by the time scale. So if this was a, so divide by 2 is easy because it's 0.5, right? For any whole number that you put there. So if it was 7, it'd be 3.5 in each. But if your time scale wasn't such that it had 1 digit on the right-hand side, it would be 3 and 3, right? It would just round it down. And then also in Verilog, if you want to divide something by 2 that could have 1 decimal place, you have to divide it by 2.0, right? Otherwise it truncates it. This is a way to generate stimulus. It's a very brute force way, right? Generally, you don't want to have something that you put in every clock cycle. I also use the wait statements in this, but it'll generate this. Is more likely as you put some kind of record in and you would iteratively read from the record. Doing something like this is difficult when you have more than one signal, right? And obviously, we have systems that have many more than one signal. In this example, the wait signal actually works well. And when you look at the wait signal, it's kind of small here, but the wait signal is waiting for 3 plus 2 times the random number. So that's going to be 3 plus 2 times a number between 0 and 1. So it could be as low as 3, as high as 5. So nominally, that's a signal that's 4 cycles long. So this gives us, and this was clock cycles, for example, then what we'd be doing is having a signal that changed on this clock, or this clock. I should stretch that out a little bit, but it'd be 3 clocks, 4 clocks, or 5 clocks. It would change. It's going to create an integer for this, right? Because we're looking at integer values. So this is how you use a random number in a time-based system, right? By moving the time. It's not just generating random values. Don't do this for the homework, but you might need to do something like this. If you, for example, had a request grant kind of cycle and you wanted to vary the time you got a grant with respect to the request, you do something like that. Synchronizing waveforms, right? Again, this isn't the best way to do it because we're using these delays and the delays are all the same. The best way to synchronize waveforms is to use like pause edge clock, right? So it will wait for the clock. This is a very common startup because it has a clock, right? It's generating a clock, 50 high, 50 low, and then here's my reset signal. It's thought as good practice that if you have a reset, and it's not necessarily the way hardware works, but if you have a reset, you bring the system up in a non-reset state, 0, set it to reset, take it out of reset. So I know how hardware works, right? In hardware, you don't have active high resets like this. You generally have active low resets. And what you do is you hold the reset low, you power on the system, and then you let reset come up. So in verification, you'd probably start the reset high, then see what happened on a low going pulse and a high going pulse. Because sometimes you can get some weird behavior there. So make sure that you not only go from reset to not reset, but also not reset to reset, right? In the middle of the system. So even if you have to toggle reset a couple times at the start. Oh, remember, that's my other reference signal is reset, right? So I showed you clock, kind of went through quick, and then resets the other one because reset's a reference signal because it gets the system to a known state. So clock is and reset. Here is something that might look familiar from implementation standpoint where you take the clock and you synchronize reset with it. Remember though, in that case, that this can have a variable delay. And what you want to make sure is that delay doesn't exceed the clock period because that would invalidate synchronizing reset that way. So test, and this is something you do at gate level too, make sure without looking at it that the designers have synchronized reset properly. You need that as verification engineer, right? It's important in system design, but it's also very important in verification that the system is a known state before you start testing. And that's what reset does. So here's the delta time. All right, the seemingly 0 delay. This is, I said the slide was out of place, and here it is. That the simulator inserts so it can queue up operations, right? So if I have 2 signals here, and one signal is derived from the other, and in a real system, there would always be some delay when I derived a signal from another signal. But where I haven't shown any delay here, they are seemingly the same, but one happens after the other. And right, so that's that. I explained that. I don't know what's wrong with this slide. Wasn't there before. All right, let's forget about this one. I'll tell you though, this is the bus functional model example, which we already know. That's weird. respin the PDFs every semester and must have done something a little different this time. So here's the abstract waveform generation. There's my device under test there. It's a multiplexer driving a flip-flop. So I'm going to have bus functional models like synchronize reset, load D0, right, that being D0, and so on, right? So we're going to write bus functional models for this, and it messed that up too. But again, think with me of what that would look like. Something that was going to load D0 would set the select line to the value that pointed to D0 and put the right value on D0. You'd run that task and it would load that value into D0, and there's a load D1. And then we would create lists of those tasks for our test case. It's what we've been talking about. I'll respin the PDFs to fix that or figure out what's wrong with it. So we get numbers from simulation, either through console type of things. Remember, we're not really looking at waveforms here. So when we extract information from the simulation, we have to do some sort of automated process. Now, the reality is we don't want to get a bunch of data. I'd like data, and we use data for some things, but what I want is to be able to predict the data and compare it. So ultimately, the output that I'm verifying is done automatically. If I want to print it, I can use write and display, and I can direct write and display to file IO. Monitor is different. So write says write this. Display says write this is formatted, but they can either go to the console. Monitor, I don't know when it's going to happen. Monitor says, okay, monitor this signal. Every time it changes, it prints it. Again, could go to a file, but I don't predict when that happens. And then they go to files. So don't rely on the list window or the wave window in this type of simulation. But really what we want is to self-check it. We'll get there. So the more output, the slower the sim runs, right? That shouldn't be a surprise. Visual inspection is not a verification process. It's useful for debugging though. Yeah, you can have a file that you can post-process, but this is what we want to do. We want to write a self-checking test bench. We want to write a test bench that takes in a bunch of stimulus, which, by the way, the stimulus is automatically generated, but I hope that's just implied by what we're talking about. Because there's really no manual method of putting in stimulus, so it's part of the test case. And then the output gets checked either against something that is formulaically related to what's coming out, so we know how to calculate the output and we compare it, or we have known data. Right? And in either case, we compare them, and the output becomes pass-fail. Right? Becomes this automated checker saying that the data passed or it failed, and this is what the mismatch was. Now, given that, we still probably record some data, but it's in a record file, right? A file that records what happened during the simulation. It's not in our final report, right? Final report says passed and we're fine. Or we might say, 10,000 iterations run, test passed, right? Something simple like that. We don't put a lot of verbose information into the final report. If it fails, even we might say it failed because of this, but we still might debug it using the full verbose report. So this is what I said. When you have known good data, synchronizing that known good data to the data coming out of your simulator can sometimes be challenging. So if my radio example, right, I have radio signals in the air and I hold up an antenna and I gather that data and then I process that data and know what the result should be. Is the latency of that processor the same as the latency of my chip? Unlikely. So synchronizing those results. And also, is the exact method of rounding that's used in that processor that predicted the output the same as the rounding that gets done? Probably not, because I use MATLAB and it's 32-bit floating point, and then my little digital circuit has 12-bit buses. And so you can't, when you compare them, simply say, does that equal that? You might have to do is that within 1 bit of that or something like that. You'll know, right? You know what you're looking for in the system, and you know what the range can be. And I use that 9-volt battery example. If I give everyone a meter and everyone a pile of 9-volt batteries, I tell them, test these to see if they're 9 volts, I get nearly a 0 yield. I have to say, make sure these are 9 volts or greater, right? So the results are within a range usually. Golden vectors, this is data that I have that I'm used to compare. I can get it from another design. So I might have, this might be derived from something, might be copied from something simply, we can get it from there. We might have a working system, we go out in the lab and we load it in with the logic analyzer. Is the clock of the logic analyzer at all related to the simulator? Probably not. So I have a synchronization problem there. I can get it from the spec. The example I use there is AES, Advanced Encryption Standard. If you go out and download the AES spec, right, you just say AES spec and you can download, it's about 50 pages long. Last 10 pages or so are plain text vectors, keys, and ciphertext. So you know if you got it right, if you implement the algorithm, which, you know, it's just kind of this complex set of equations, and then you put in their plain text and their key, and you should get the same ciphertext out. But of course, it's so complicated, you don't. So what they actually do is they give you pages of intermediate data, so you can see where you went wrong, right? So that's spec data. Get it from hardware modeling, put an actual chip in, right? I talked about that when I talked about hardware modeler. And sometimes manufacturers will give you expected kinds of data. So what's the problem? You have to verify that they're right? You gather this data, you have to make sure that you gathered it properly and it's the data that you expected. Every time they change, you have to regather the data. And a lot of times it's gathering it and then somehow processing it so it can be test vectors. So there's maintenance, right? I talked about that. You know, people go out in the field, they gather all this data and they come up with terabyte drives, and, you know, it has to be cataloged and organized, and inevitably things aren't the way you'd like them to be. And then what I keep saying is you have to synchronize them. Right? The clock domain that you gathered in is probably different from the clock domain in your simulator. So this is a different way of doing it, where you have your stimulus and you generate it onto your device under verification, and then you generate it on a behavioral model. So you've effectively designed the system twice. The designers did this, the verifiers did this, and you compare the results. Is the latency of this exactly the same as latency of that? It could be if you go to a lot of work in the behavioral model. One of the very first things I said tonight was you don't worry about a lot of that stuff in the behavioral model. So you can have a timing problem in that comparison. You might have to put extra synchronization there to get it to work right. And know that you're not putting the extra synchronization in to make it work. So this, when I say runtime verification, I generate stimulus and the self-checker knows what the output should be, right? So it's not a reference model. It's just that the self-checker knows what it should be. Now, in this case, this isn't terribly practical. This is simple generation and simple response checking. We need complex response checking here. Complex response checking is response checking that knows what the stimulus was. Complex stimulus, by the way, is stimulus that knows what the result was. Maybe it just needs to know what it's done, but it needs to know something about it. So there's really no such thing as simple stimulus. I think if I had to give you one example of simple stimulus, it would be clock and reset. But everything else, the stimulus has to know something about the state of the system, and the response definitely has to know, especially in a random, constrained random test, the response checker really needs to know what's going in. Maybe my MATLAB example, where it generated a whole bunch of data and then knew what data would come out, that you could do that in this simple way. But there's got to be some feedback and feed forward in this process. So the self-checker needs to be verified, right? Because if it isn't right, you don't know where the error comes from. You can use a self-checker with post-processing, but it's really nice to have it online, right? To have it working with the system, because then you know that it fails a lot sooner than if you have to run the whole simulation and check it after from a file. So you hear this called autonomous self-checking, right? That it doesn't need external value. Not only does it have to work with correct conditions, but it has to work with errors. So if you're also creating stimulus that randomly inserts errors, about an hour ago I was talking about that, then the self-checker has to deal with that as well. It just adds some more complexity to it. The checker can be harder to build than the design itself. hence 2 to 3 times. So here's complex stimulus. So when I do a request, I get a grant. The grant has to happen within these windows. And the response checker has to know that the request happened. And the stimulus has to know the grant happened, because when grant happens, the request goes away. So there has to be information in both directions. Here's basically what I just showed. Think of the examples that I've given you, right? The scoreboard is in itself complex response checker, because you're taking the stimulus, you're putting it into the scoreboard, and the response checker is adding things into the scoreboard, which compares everything. So if the input never happened to the scoreboard, which is part of complex response, then the response checker would have nothing to check against. So it's both ways. I would say complex response is required. Complex stimulus is popular, right? So what happens if you have something that looks for an input to know what to do, and you have that in both directions? So you have a complex checker that's looking for something on the stimulus generator, and it's effectively waiting for that. And then the stimulus generator is waiting for something to happen on the response. You could hang and you get a deadlock, right? And deadlocks are common in like networking systems. We have bridges, and you send something across the bridge, it's waiting for an acknowledgement, but the other side sends something in the other way on the bridge, it's waiting for the acknowledgement, but the side that's sending isn't going to send the acknowledge because it's waiting for the acknowledge to come from the other side. And it hangs, right? And obviously that's not a condition you can deal with. So when you're building this and you're building complex stimulus and complex response, if you're not careful about those things, you'll find out what a deadlock is, because the system will just stop working. And then you'll see that both sides are waiting for data. So you can handle deadlocks with basically 2 ways, and maybe a combination of 2 ways. One's a timer, that if you have a request that gets sent and it doesn't get a response within a certain amount of time, it gives up. Now, you think, boy, that'd be an interesting thing to put in a chip. And if it wasn't in the chip, you'd have to test it. But you also have to put that in your BFMs, right, in your stimulus and response checker. And then the other thing is something that just senses that case, that looks to see that there's a request in both directions for the same, the opposite thing. And that's a bad situation. Now, the DUT has to have a proper way of getting out of deadlocks. But sometimes it doesn't even matter in the DUT, because there's no complex stimulus, complex response relationship in the DUT, but you've built it into your test bench. So deadlocks. You don't have to understand it, but think of me when it happens to you. And it will happen, even if you plan for it. Okay. You think of asynchronous in 2 ways. Asynchronous is, it happens on a clock cycle, but I don't know which clock cycle. Or it happens somewhere within the clock period. So we'll talk about asynchronous, when we get around gate level stuff, we'll talk about asynchronous verification, all the reasons why it's hard. Here, when we talk about asynchronous stimulus, we're talking about something that happens and it's technically synchronous, but we don't know when it's going to happen. So the response checker has to be more of a monitoring device. Now, in the homework kind of example, that's what the monitor basically is, right? It doesn't know when the data is coming. It just gets sent. And that's fine. But in a case where there's more than one source, now the monitor has to be smarter, because it doesn't know what the order things are going to come in. Okay. So another quick review of bus functional models that keeps coming up. So it's encapsulation of bus stimulus. Yes, we know that. Must be behavioral code because feedback is essential. Yeah, maybe it would. A read, modify, write. This is kind of the bidirectional bus that you have on the homework assignment, right? You have to have something that can both read and write. So it's monitoring the bus and generating things on the bus. So it's not the full read, modify, write, but at least it has to be capable of bidirectional. come from, hopefully this matches, third-party models, processor interfaces, and code that you write. Beginning class, we had a list. I think the list had 4 things, though. Okay, questions? We're good? We'll just keep trudging forward here. Okay. So I mentioned this earlier, that you can have test cases that are the same. But for some reason, when you run them in different ways, they produce different coverage. And that's what we're trying to do. So we want to write bus functional models, never change them. And we want to run test cases that cover all our features, but we want to write as few test cases as possible. So to do that, we make the test cases configurable. And I'm not going to talk about what it is to configure a test case. We'll talk about what kinds of things we would want to configure. So for example, if I have a DUT that just blatantly has configuration registers in it, then we might have a test case that we run multiple times with a different set of configurations. So we write to a bunch of registers in the chip that sets it up in a way that is a scenario that we want to test, and we run the test case. And then with a different set of configurations, we run the test case again. If we have a thick bus functional model, we may have some configuration there. Now, this is a little different. And I'll give you the wild example, but remember the Ethernet packet generator that I talked about, and it had various packet size, destination, source, all that kind of stuff in it. And that called a low-level bus functional model that just sent out bytes, right? But it was the big bus functional model. Let's say I wanted to build a network packet generator, and it had a configuration that was Ethernet, and a configuration that was Wi-Fi, obviously after the receiver, and a configuration that was something that doesn't exist, token ring, right? All these so I'd have one bus functional model that I could configure in different ways. Now, I don't know if I like that, but what I could do is, let's say there was version 1 Ethernet and version 2 Ethernet and version 3. So now I could have that Ethernet packet generator, but I could set it for different configurations to support different compatibilities, right? Different specs for the same Ethernet thing. So you don't want to go crazy with it, but a lot of times you can get away with a general bus functional model that you can configure for different versions of what you're trying to do. So I went to full extent. That's not a good idea, but something that's configurable. And then also you might consider having a test case that randomly configures the DUT, right? Not necessarily this. So here's the complex response. I talked about this. So complex response is a response that knows what the stimulus was. So know the 4 things: simple stimulus, simple response. Simple stimulus is just generate a bunch of data. Maybe you generate random data, but you generate it not caring about what's going on in the rest of the system. You just keep going. Simple response is you just look at the output and make sure it's good. It's hard to do. It's hard to look at the output and know what it's doing the right thing unless you know what the input was. That's complex response. Complex response is response checking that knows what the input is. Okay? In different ways. All kinds of stuff, right? Consider failure modes. We always say that. We want to synchronize operations, so we do a fork and a join, so everything's running in parallel. We already do that. You probably would do that even if it wasn't complex. And then the output checkers are, right, they're all bus functional models, especially. Everybody hates bidirectional interfaces. Back-end ASIC people hate them. The people who write tests for manufacturing tests hate them. Designers hate them because it's multiple pins to connect to one pin. And verification engineers hate them too. And really the reason why you hate this stuff is not because it's input and output, right? Which is, a stimulus and response on one pin, but you don't know if it's enabled or not. Now, remember black box, white box, gray box? The little bit of gray that's in here might be that enable line. That you steal that enable line so you know if it's enabled at the time it's supposed to be enabled. You can, maybe do a test to see if it's Z. That's just more code that has to go into your monitor. So it's hard, but you have to do it. And, I don't have a magic formula for it, but we have device under verification, some other code, and then stimulus and response, and feedback to the stimulus from the response. So it's complex. So what's this? You know what this is? It's a bidirectional driver. So if you look at the code for a bidirectional driver, that's what this is. It's kind of the dual of what's in here. It's a behavioral model of it, but it's the same kind of thing. So it's a driver this way, a driver this way, the receiver, the transmitter into here can be tri-stated. You got more checks in there because you have to check to see whether it's high or low. I don't really see when it's enabled or not, but that has to come from the stimulus. So there's really two things coming from the stimulus. I can't generalize this because it's going to be different for however you set up your tri-state drivers. So just know that that's harder, right? That bidirectional buses are harder. And it's harder because you don't know what direction they're in just by looking at it. This is a little bit of redundancy. So if I have stimulus, I can put it through this like preprocessor and it goes, this has nothing to do with bidirectional necessarily now. Stimulus, it gets reformatted, goes into device under verification response checking. And then from that stimulus, I just produce a value, right? I predict the value from this and it goes in there. Stimulus here, I can go through the FIFO behavioral model, for example, and then the FIFO test, right? And this is just verifying that what goes in comes out in the same order because that's what FIFOs do. So think of that as the behavioral model and the DUT from before, just a little bit of a real example. I can have a big networking system where I have a bunch of stimulus generators that are here's my random generator, right? So it randomly orchestrates what's going in here. I get packets out, and then I get a bunch of response checkers which just say, oh, this is a packet, and create a record for the packet. And it goes into this thing that looks at it. But of course, I have to have feedback. The other view of this was a view that I had of the FIFO where this thing right here is a scoreboard. This I get from the book. So stimulus into a data transmogrifier. I had to look up transmogrifier. Transmogrification is converting from one animal to another like a werewolf. Look it up. I saw it there and thought, oh, I got to put this in the slides. So I have, this is a nice general view. I have stimulus. It goes through a data transmogrification and a different data transmogrification. And I check to make sure they're the same. We started out the class with this type. And this is very common. The DUT, this behavioral model of the DUT. What's the best way? Because you've shown us like 3 different ways to do this. You've shown us this way. You've shown us known data in, known data out. You've shown complex stimulus in a scoreboard. What's the best way? The answer is it depends. It depends on the type of thing you're doing. Something like this would work well in my processor example. Something like the complex stimulus complex response would work, like the scoreboard example would work well here, right? That's why I showed it there. Something like just the straight through where I knew what the response was is my data processing example. So it depends. And there's a good chance that when you actually do something, you're going to have combinations of these things. A transaction level interface is a bus functional model. Right? That's what bus functional models do. They take signals and bring them up to a transaction level interface. It wasn't a TLM, was the acronym from the first half transaction level model, which is also what we had for bus functional models. So, and I put out the different terms for the same thing because I tend to always use bus functional models, but not everyone does that. So the bus functional models are common, but I don't want you to see transaction level interface and not know that it's what I've been talking about is a bus functional model. Wow. I thought there were 406 slides. I guess there's only 401. Questions? No questions. So homework is due next time. If you didn't get homework 4 exactly working, make a credible attempt at homework 5 that shows what you would do. And show me that it compiles and that it, maybe puts the dot and reset and things like that, and we'll be good. If I noted on your homework that you weren't doing the right thing, then you got to get around to doing the right thing so you have bus functional models to use for this. But on that, you're good. So I think next week is here too. And then we start alternating again. Questions? It'll be my younger brother next week too, teaching the class. You'll figure that out. We're good? Okay, have a good night. Thank you.